Good morning, everyone. I'm Charles Jeremy D. Song Song, and I'm about to discuss the turbine engine lubrication system. So first, turbine engine lubrication system. Both both wet and dry sump lubrication systems are used in gas turbine engines. Turbines engines oil system can be also classified as a pressure relief system that maintains a somewhat constant pressure. That full flow type of system in which the pressure varies with the engine speed and total loss system, used in engines that are for short duration operation, target drones, missiles, and etc. The exhaust turbine bearing is the most critical lubricating point in a gas turbine engine because of the high temperature normal present. Types of oils in turbine engines. The two types of synthetic oils are currently used in turbine engines is type 1 MIL-L-7808 and type 2 MIL-L-23699. Type 1 synthetic oil is an alkyl diester oil with a 3 centi-stroke rating. This type of synthetic oil has a very low viscosity and was used primarily in turbine engines. Type 2 synthetic oil is a polyester lubricant that has a 5 centi-stroke rating and is used in modern turbine engines. So the difference in the two synthetic oil is the type 1 is for the old model of turbine engines and the type 2 is used in the modern turbine engines. The turbine lubrication system components. These are the following components. Description include most of the various turbine lubrication system. Engine oil system varies somewhat according to the engine model and manufacturer. Not all of these components are necessarily found in one system. So next, we will discuss the components of a lubrication system. First is the oil tank. Although the dry sump and the oil reservoir of a dry sump system is typically constructed of form sheet, aluminum, or stainless steel, and furnish a constant supply of oil to the engine during all approved flight maneuvers. As mentioned earlier, in a dry sump system, the oil reservoir can be mounted externally or internally. When mounted externally, the reservoir might be attached to the engine case or mounted inside the aircraft structure. When mounted internally, oil reservoir is formed by an internal space or cavity within the engine structure. Common location for internal oil reservoir includes cavities between major cases sections and propeller reduction gearboxes. Use an oil tank that contains most of the oil supply. A small sump is usually included on the engine to hold a small supply of oil. So dry sump is used when we have an oil tank, and wet sump is the oil is inside the engine. Uh, the difference between the dry sump and the wet sump is the dry sump is heavier and yeah, it is heavier because it needs another oil tank, while the wet sump is mounted internally in the engine and in a view of a typical oil tank is shown. It is designed to furnish constant supply of oil to the engine during any aircraft attitude. This is done by swivel outlet assembly mounted inside the tank, a horizontal baffle mounted in the center of the tank, two flapper check valves mounted on the baffle, and a positive vent system. As you can see in the picture here, this is what an oil tank looks like. All oil tanks are provided with the expansion phase. This allows expansion of the oil after heat is absorbed from the bearings and gears and after the oil foams as a result of circulating through the system. Some tanks also incorporate a the aerator tray for separating air from the oil returned to the top of the tank by scavenger system. Usually these deaerators are the type are the kind type in which oil enters at a tangent. Next is oil pump. Oil pump is designed to supply oil under pressure to the parts of the engine that requires lubrications, then circulate the oil through coolers as needed, and return the oil to the oil tank. Many oil pumps consist of a not only a pressure supply element but also a scavenge element, such as in dry sump system. However, there are some oil pumps that serve a single function. That is, they either supply or scavenge the oil. The number of pumping elements, two gear that pump oil, pressure, and scavenge depend largely on the type of model of the engine. The pumps may be one of several types, each type having certain advantages and limitations. The two most common oil pumps are the gear and gear rotor, with the gear type being the most commonly used. Types of gear pump is the uh of oil pump is gear pump. The gear type oil pump has only two elements, one for pressure oil and one for scavenging. However, some types of pumps may have several elements, one or more elements for pressure and two or more for scavenging. Gear rotor pump. The gear rotor pump, like the gear pump, usually contains a single element for oil pressure and several elements for scavenging oil. Each of the element pressure and scavenge is almost identical in shape. However, the capacity of element can be controlled by varying the size of the gerotor system. Next is the vane pump. A vane pump uses sliding vanes in an eccentric rotor to move fluid. The rotor drive shaft and eccentric rotor from a single rotating part. The driving vanes, which form the pump chambers. The sliding vanes move in and out of the eccentric rotor, increasing the chamber volume when approaching the oil inlet. As a chamber rotates past the inlet, the eccentric shape of the rotor reduces. The volume between the vane and oil is forced out of the pump. The pump used in an oil system, the sliding vane pump, is considered the most tolerant of the three. Sliding vane pumps are ideal for use in a scavenge system. This is what a gear pump looks like, and this is what the gear rotor pump looks like, and this is the vane pump. As you can see the difference, you can clearly see the difference of the different kinds of oil pump. Next is turbine oil filters. Filters are an important part of the lubrication systems because they remove foreign particles that may be in the oil. This is particularly important in gas turbines as a very high engine speeds are attained. The anti-friction types of ball and roller bearings would become damaged quite rapidly if lubricated with contaminated oil. So we use these filters so that we will not have any damage on the roller bearings and ball bearings. These several types of applications of filters used for filtrating the turbine lubricating oil. The filtering elements come in a variety of configuration and mesh sizes. Mesh sizes are measured in microns, which is linear measurement equal to 1 millionth of a meter. A main oil strainer filter element is shown on the left. Uh, Oil normally flows through the filter element from the outside into the filter body. One type of oil filter uses a replaceable laminated paper element, while other uses a very fine stainless steel metal mesh of about 25 to 35 microns. Next is the oil pressure regulating valve. Most turbine engine oil systems are the pressure regulating type system that keeps the pressure fairly constant. An oil pressure regulating valve is included in the oil system on the pressure side of the pressure pump. A regulating valve system controls the system pressure to a limited pressure within the system. It is more of a regulating valve than a relief valve because it keeps the pressure in the system within certain limits other than only opening when the absolute maximum pressure of the system is exceeded. We use oil pressure regulating valve when uh the pressure system within the certain limits that only opening the when the absolute maximum pressure of the system is exceeded. Oil pressure relief valve. Some large turbofan oil systems do not have a regulating valve. The system pressure varies with engine RPM and pump speed. There is a wide range of pressure in the system. A relief valve is used to relieve pressure only if it is exceeds the maximum limit for the system. This true relief valve system is preset to relieve pressures and bypass the oil back to the inlet side of the oil pump whenever the pressure exceeds the maximum preset system limit. The relief valve is especially important when oil coolers are incorporated bleed air from the compressor to the oil nozzle outlet. Next component is the oil jet. Oil jet or nozzles are located in the pressure lines adjacent to or within the bearing compartment and rotor shaft couplings. The oil from these nozzles is delivered in the form of an atomized spray. Some engines use an air oil mist spray that is produced by tapping high pressure bleed air from the compressor to the oil nozzle outlet. This method is considered adequate for ball and roller bearings. However, the solid soil spray method is considered the better of the two methods. The oil jets are easily clogged because of the small orifice in their tips. Consequently, the oil must be free from any foreign particles. If the last chance filter in the oil jet should become clogged, bearing failure usually results since nozzles are not accessible for cleaning except during engine maintenance. To prevent damage from the clogged oil jets, main oil filters are checked frequently for contaminations. Lubrication system instrumentation. Gauge connection provisions are incorporated in the oil system for oil pressure, oil quantity, low oil pressure, oil filter differential pressure switch, and oil temperature. The oil pressure gauge measures the pressure of the lubricant as it leaves the pump and enters the pressure system. The oil pressure transmitter connection is located in the pressure line between the pump and various points of lubrication. An electronic sensor is placed to send a signal to the full authority digital engine control FADEC control unit and through the engine indicating and crew alerting system EICAS computer and onto the display in the flight deck. The low oil pressure switch alerts the crew if the oil pressure falls below a certain pressure during engine operation. The differential oil pressure switch alerts the flight crew and an impending oil filter bypass because of a clogged filter. Lubrication system, breather system, vents. Breather subsystems are used to remove excess air from the bearing cavities and return the air to the oil tank where it is separated from any oil mix in the vapor of air and oil by the aerator. Then the air is vented overboard and back to the atmosphere. All engine bearing compartments, oil tanks, and accessory cases are vented together so the pressure in the system remains the same. The vent in an oil tank keeps the pressure within the tank from rising above or falling below that of the outside atmosphere. However, the vent may be routed through a check relief valve that is preset to maintain a slight approximately 4 psi pressure on the oil to assure a positive flow to the oil pump inlet. Lubrication system check valves. Check valves are sometimes installed in the oil supply lines of dry sump oil system to prevent reservoir oil from seeping by gravity through the oil pump elements and high pressure lines into the engine after shutdown. Check valves by stopping flow in an opposite direction. It prevents accumulation of undue amounts of oil in the accessory gearbox, compressor rear housing, and combustion chamber. Such accumulation could cause excessive loading of the accessory drive gears during starts, contamination of the cabin, pressurization air, or internal oil fires. Check valves are usually the spring-loaded ball and socket type constructed for free flow of pressure oil. The pressure required to open this valve varies, but the valve generally requires from 2 to 5 psi to permit oil to flow to the bearings. Next is oil cooler. Dry sump lubrication system requires cooler for several reasons. First, air cooling of bearing by using compressor bleed air is not sufficient to cool the turbine bearing cavities because of the heat present in the area of the turbine bearings. Second, the large turbofan engines normally requires a greater number of bearings, which means that more heat transferred to the oil. Consequently, the oil coolers are the only means of dissipating the oil heat. Air oil coolers. Two basic types of oil coolers in the general use are the air-cooled and fuel-cooled. Air oil coolers are used in the lubricating system of some turbine engines to reduce the temperature of the oil to a degree suitable for recirculation through the system. The air-cooled oil cooler is normally installed at the forward end of the engine. It is similarly in construction and operation of to the air-cooled cooler used on reciprocating engines. Air oil cooler is usually included in a dry sump system, while the fuel oil coolers acts as a fuel oil heat exchanger in that the fuel cools the hot oil and the oil heats the fuel for combustion. Fuel flowing to the engine must pass through the heat exchanger. However, there is a thermostatic valve that controls the oil flow, and oil may bypass the cooler if no cooling is needed. The fuel or oil heat exchanger consists of a series of joint tubes with an inlet and outlet port. The oil enters the inlet port, moves around the fuel tubes, and goes out the oil outlet port. This is what air oil cooler looks like, and this is how the fuel oil coolers look as the fuel inlet goes in the two tubes. It passes through the tubes. It goes out in the fuel outlet. As the fuel goes in the tubes, the oil temperature control valves controls the temperature of the air inside the tubes, and the oil returns back to the oil pump. Next is de-oilers. The de-oilers removes the oil from the breather air. The breather air goes into an impeller that turns the de-oiler housing. Centrifugal force drives the oil towards the outer wall of the impeller. Then the oil drains from the de-oiler into a sump or oil tank. Because the air is much lighter than the oil, it goes through the center of the impeller and is vented. Magic chip detectors. Magic chip detectors are used in the oil system to detect and catch various magic particles present in the oil. Scavenged oil generally flows past chip detectors, so any magnetic particles are attracted and stick to the chip detectors. Chip detectors are placed in several locations, but generally are in the scavenge lines for each scavenge pump, oil tank, and in the oil sumps. Some engines have several detectors to one detector. During maintenance, the chip detectors are removed from the engine and inspected for metal. If none is found, the detector is cleaned, replaced, and safety wired. If metal is found on a chip detector, an investigation should be made to find the source of the metal on the chip. Thank you for so let's go back and let's check if you all still remember the components of a turbine lubrication system. First is the oil tank. We use oil tanks so that first is the oil tank which has a dry sump and wet sump. Next is oil pump. We use oil pump to supply oil under pressure to the parts of the engine that requires lubrication, then circulate the oil through coolers as needed, and return the oil to the oil tank. Next is the oil pumps. Oil pumps is types of oil pumps: gear pump, gerotor pump, and vane pump. The gear type oil pump has only two elements, one for pressure oil and one for scavenging. Gerotor pump, each set of gerotor is separated by a steel plate, making each set an individual pumping unit consists of an inner and an outer element. The small star-shaped inner element has external lobes that fit within the and are matched with the outer element that has internal lobes. Vane pump. A vane pump uses sliding vanes in an eccentric rotor to move the rotor drive shaft and eccentric rotor from a single rotating part. This is what they are look like. Next is turbine oil filters. Filters are an important part of the lubrication system because they remove foreign particles that may be in the oil, particularly important in gas turbine as we need a high engine speed so that the anti-friction types of ball and roller bearings would become damaged quite rapidly if we did not filter the contaminated oil. Oil pressure regulating valve. Most turbine engine oil system are the pressure regulating valve system that keeps the pressure fairly constant. An oil pressure regulator is included in the oil system on the pressure side of the pressure pump. Oil pressure relief valve. Yeah. Some large turbofan oil systems do not have regulating valve. System pressure varies with engine RPM and pump speed. There is a wide range of pressure in the system. A relief valve is used to relieve pressure only if it exceeds the maximum limit for the system. Next is the oil jet. Oil jet or nozzles are located in the pressure line adjacent to or within the bearing compartments and rotor shaft couplings. The oil from these nozzles is delivered in the form of an atomized spray. Lubrication system instrumentation. Gauge connection provisions are incorporated in the oil system for oil pressure, oil quantity, low oil pressure, oil filter differential, pressure switch, and oil temperature. Next is the lubrication system, breather system. Breather subsystems are used to remove excess air from the bearing cavities and return the air to the oil tank where it is separated from any oil mix in the vapor of air and oil by the deaerator. Next is the lubrication system check valves. Check valves are sometimes installed in the oil supply lines of dry sump oil system to prevent reservoir oil from seeping by gravity through the oil pump elements and high pressure lines into the engine after shutdown. Oil cooler. Dry sump lubrication system requires coolers for several reasons. First, air cooling is occurring by using compressor bleed air is not sufficient to cool the turbine bearings cavities because of the heat present in the turbine bearings. Types of oil coolers are air oil cooler and fuel oil coolers. Air oil coolers are used in the lubrication system of turbine engines to reduce temperature of the oil into a degree suitable for recirculation through the system. And fuel oil coolers. Fuel oil coolers acts as a fuel oil heat exchanger. In the fuel cools the hot oil and the oil heats the fuel for combustion. Next is the de-oiler. The de-oil removes the oil from the breather air. The breather air goes into an impeller that turns in the de-oiler housing. Centrifugal force drives the oil towards the outer wall of the impeller. Next, the magnetic chip detector. Magnetic chip detectors are used in the oil system to detect and catch ferrous magnetic particles present in the oil. Scavenged oil generally flow past chip detectors so any magnetic particles are attracted and stick to the chip detector. Again, thank you for